Can the strange world of quantum mechanics be used to explain the behavior of everyday large objects? This provocative question sits at the intersection of quantum and classical physics. While classical mechanics adeptly describes the movements and interactions of everyday objects we encounter, the atomic realm dances to the tune of quantum mechanics. Bridging these two domains offers not only profound insights into the nature of reality, but also paves the way for groundbreaking advancements in sensing technologies, particularly in measuring gravitational forces. Recently, a pioneering team of researchers from ETH Zurich in Switzerland and the Institute of Photonic Sciences in Barcelona has made an exciting breakthrough. They have pushed the envelope in understanding how the wave properties of larger particles, specifically nanoparticles, facilitate this essential connection, creating a bridge between the quantum world, where particles can exhibit wave-like behaviors, and the classical realm of much larger objects. Quantum mechanics suggests that all objects, no matter how large, can exhibit wave-like characteristics. However, this behavior is typically confined to remarkably small scales due to a parameter known as the coherence length. This coherence length, which measures the spatial extent of wave-like behavior, is significantly shorter than the dimensions of large objects, making it difficult to observe quantum phenomena in anything that isn't a tiny particle. According to lead researcher Massimiliano Rossi, achieving observable quantum behavior in larger systems necessitates a concurrent increase in both the object's mass and its coherence length. This intriguing ambition inspired their latest study, which was published in the well-regarded journal Physical Review Letters. The researchers focused their efforts on silicon nanoparticles, each about 100 nanometers in diameter. They leveraged a focused laser beam to hold and levitate these nanoparticles in a vacuum. The nanoparticles inherently scatter light from the laser, with variations in the phase of the scattered photons carrying vital information regarding the position of the particle's center of mass. This information was then utilized in a feedback loop system. Electric fields were applied to cool the nanoparticles down, nudging them closer to their quantum ground state. A colder sample is indicative of a purer quantum state, enabling longer coherence lengths and, consequently, a greater manifestation of wave-like behavior. Initially, the team recorded a coherence length of 21 picometers, pm. That's an astonishing 21 trillionths of a meter. To extend this coherence length, the researchers engaged in precise manipulation of the laser light. They began their experiments with high-intensity light, which provided a strong harmonic potential for the nanoparticles, akin to a marble stuck at the bottom of a steep bowl. A notable advantage of using laser-induced confinement is the ability to easily adjust the bowl's curvature by modulating the laser's power. During the experiment, the researchers sequentially reduced the laser power in 2 distinct pulses, resulting in the bowl becoming gradually shallower. This adjustment allowed the marble, in this case, the nanoparticles, to roam more freely within the potential well. As a result, the coherence length expanded impressively to 73 picometers, surpassing the initial measurement more than threefold. One of the significant hurdles that the researchers faced was managing decoherence, the process that obliterates quantum information. Decoherence occurs when a nanoparticle interacts with its surrounding environment, leading it to correlate with numerous variables that are difficult to measure. Consequently, this interaction results in a randomization of the particle's motion, compelling a transition toward classical descriptions of its behavior, effectively erasing the quantum characteristics. To mitigate decoherence, it was crucial for the team to expand the coherence length at a rate faster than decoherence itself could occur. The researchers meticulously examined every potential source of decoherence and worked to minimize them. They identified laser light scattering as the primary source of decoherence and effectively reduced it during the crucial expansion pulses by lowering the laser's power. While the achieved coherence length of 73 picometers falls significantly short compared to the size of the nanoparticles, 100 nanometers, it's essential to note that Rossi believes there are no fundamental barriers that would prevent the realization of coherence lengths on the nanometer scale. One potential avenue for future research could involve utilizing additional expansion pulses to further extend coherence lengths. However, as coherence lengths increase, the challenge of overcoming decoherence also escalates. To address this, researchers are considering the use of hybrid traps that utilize both optical and electric fields to confine the nanoparticles, as the latter could diminish decoherence arising from light scattering. Rossi is already pursuing this innovative approach through his newly established research group at Delft University of Technology in the Netherlands. As we continue to explore the realms of quantum mechanics, the possibilities are vast. What are your thoughts on merging quantum physics with classical mechanics? Do you think it's feasible to observe quantum behavior in larger entities effectively? Let's engage in the comments below.